Today we're going to do section 1.5, solution sets of linear systems. A homogeneous system is in the form AX equals 0. A is an m by n matrix and 0 is the 0 vector in Rn. Let's look at example 1. Write the corresponding matrix AX equals 0. Does the matrix have a trivial solution? Do non-trivial solutions exist? So the first thing we're going to do is we're going to rewrite this matrix in the form 1, 2, 10, 20 times x1, x2 equals 0, 0. So here, x equals 0, or we know that our x is the 0 vector. This means this is our trivial solution here. So the homogeneous solution AX equals 0 always has the trivial solution x equals 0. So just as a note, the homogeneous system AX equals 0 always has the trivial solution x equals 0. If we want to go through and find the non-trivial solutions, or that non-trivial solutions exist, we can go ahead and row reduce this. So I'm going to take my augmented matrix, I'm going to row reduce this to 1, 0, 10, 0, 0, 0. And non-trivial solutions exist. This is a consistent system with a free variable. So it has infinitely many solutions. x1 plus 10 x2 equals 0 goes to x1 equals negative 10x2, where x2 is a free variable. A homogeneous equation, AX equals 0, has non-trivial solutions if and only if the system of equations has at least one free variable. Let's go ahead and look at example 2. Determine if the following homogeneous system has non-trivial solutions. So it is actually missing and describe the solution set. Okay, so the first thing we want to do is have our augmented matrix, and we want to solve for that. And then you'll be able to go ahead and describe the solution set from there. So I have 2, 4, 4, 8, negative 6, negative 10, 0, 0. I can first take 1/2 of row 1 to get that lead in 1. Then I can take negative row 1 and add it to row 2, or -4 times row 1 and add it to row 2 to eliminate that 4 below. So I'm not doing anything to row 1. I'm taking -4 row 1 and adding it to the row below, and I'd get 0, 0, 2, 0. And from there, I'm going to take half of row 2, leave row 1 alone, 1, 2, -3, 0, 0, 0, 1, 0. And then finally, I can take 3 times row 2 and add it to row 1 to eliminate that -3. So with this, I would have x1 equals -2x2. x2 is a free variable. x3 equals 0. And since x2 is a free variable, there's non-trivial solutions exist. And what we could do is we could describe this as follows. So you will see this notation. We would have x equals x1, x2, x3. And we said that x1 is -2x2, x2 is x2, and x3 is 0, which then could be described as x2 is -2, 1, 0. And further, sometimes you will see it go further, and they would describe this as v. And you could describe this as x2 times v. Let's look at example 3. Describe the solution set of the following system. So when we're looking at this, this is 2x1 plus 4x2 minus 6x3 equals 0. And 4x1 plus 8x2 minus 10x3 equals 4. This has the same left side as example 2. What happens here is this is no longer 0, it's a 4. So things are going to change, and we're going to describe what that change is. So we need to go and row reduce this again. If you want to pause and practice row reducing yourself, go ahead and do that. Set up your augmented matrix. And I can go ahead and again take half of row 1 to get that lead in 1. And then again, I can take -4 of row 1 and add it to row 2. From here, I can do half of row 2 again. And lastly, 3 times row 2 and add it to row 1 to get rid of that -3 above. So with this, x1 would be 6 minus 2x2. x2 would be my free variable. And x3 would equal 2. So when writing this out like this, x1 we said was 6 minus 2x2. X2 is x2, and x3 equals 2. This would be 6, 0, 2, because those are my constants, plus x2 times negative 2, 1, 0. If we describe this as P and this as V, this would then equal P plus x2V. So how did this change compared to the previous one? We added a constant to it. And when that happens, these are parallel. So this is parallel to our previous answer. So this is parallel to AX equals 0 and AX equals B. So let's look at theorem 6. Suppose the equation AX equals B is consistent for some given B. And let P be a solution. The solution set of AX equals B is the set of all vectors in the form W equals P plus V of n, where V sub n is any solution to the homogeneous solution AX equals 0. Let me just fix this for a minute for you guys. So to describe the solution set of two x1 minus 4x2 minus 4x3 equals 0, and compare it to the solution set of 2x1 minus 4x2 minus 4x3 equals 6. So this is just like our previous example, almost. So let's go ahead and have our augmented matrix. So our corresponding augmented matrix would be 2, negative 4, negative 4, 0. And what we can do is we can 1/2 all of this, and we would get 1, negative 2, negative 2, 0. So we would have x1 equals 2x2 plus 2x3. x2 is free, and x3 is free. So if I were to put this in the form of V, I would have x2 so go over here. So I'd have V would be times 2x2 plus 2x3. And then x2 and x3 because they're free. This would just be x2 times 2, 1, 0, plus x3 times 2, 0, 1. Okay, so then we need to look at 2, negative 4, and 6. This row reduces to 1, negative 2, 3. So I'd have x1 equals 2x2 plus 2x3. x2 is free, and x3 is free. So when I'm setting this up, I'd have 2x2 plus 2x3, x2 and x3. This would be x2 times 2, 1, 0. Plus x3 times 2, 0, 1 plus 3, 0, 0. A lot of times you'll see that up first, front and center. And I forgot my 3 there. So this right here would be parallel solution sets of those in the form of ax equals 0 and ax equals b. So in closing, writing a solution set of a consistent system in parametric vector form. 1, you would row reduce the augmented matrix to reduced echelon form. 2, express each basic variable in terms of any free variable appearing in an equation. 3, write a typical solution x as a vector of whose entries depend on the free variables, if any, and then decompose x into a linear combination of vectors with numerical entries, using the free variables as parameters.